And the next topic I'd like to talk about is actually when you have shorted termination. That is, if you take the transmission line, instead of putting a load at the other end of the transmission line, you put a short. And this has many engineering applications. And if you do that, what you do then is, let me move this slide up so that it will be next to the previous slide. So if you take this formula and change ZL to 0, okay, so if I take the previous formula from the slide and change the load impedance to this to be 0, which is the impedance of a shorted transmission line at the end. And then you can look at the formula. This term will go away, that term will go away. And then you can see that ZL is actually Z minus L would be equal to J Z naught tangent of beta L. Okay, L is the length. This point over here. Okay. So if you plot this formula, Z naught is a real number for a lossless line. I remind you that Z naught is a real number, is given by this. And then it looks something like that. It will be like the plot of a tangent. And it will have an inductive part and a capacitive part. And when the length is very small, then the transmission line will have an impedance that looks like that of an inductor. However, if you make the length of the transmission line longer, it actually can resonate. And when it resonates, it will have infinite impedance. Just like an LC tank circuit, you probably have seen this before, that if you have, say, an LC tank circuit, you probably learned that when this thing is at resonance, you see an infinite impedance. So you can say that this point here is when this circuit hits a resonance point, and it will have infinite impedance. The interesting thing about transmission line is that the moment you go right to the right of this resonance point, you have a negative reactance. You have a negative reactance. If I call this to be something like Jx, okay, X to be the reactance of the line, then you can see that when something is negative, you probably learn from your circuit theory that impedance of a capacitor is 1 over J omega C is minus J 1 over omega C. So a capacitor has negative reactance. So we call that this part of the line is capacitive. Whereas if you have an inductor, you probably know that the Z of an inductor is J omega L from the circuit theory course, and that the inductor has positive reactance, and hence you call this part of the line to be inductive. And it swaps back and forth depending on the length of the line, because when something is inductive, it means that there's a lot of magnetic field stored in the system. When there's something is capacitive, it means that there's lots of electric field storage in the system. And it swaps back and forth because there could be charge accumulation and standing wave or wave pattern on this transmission line that give rise to this standing wave pattern. What is remarkable is that when you have a very short line, okay, you know that when beta L is very small, you can approximate this as beta L. It's a trigonometric identity that you learned in high school. Okay, the argument of a tangent function is small, it can be approximated by that. And then you have this formula, Z of minus L is J Z naught Z naught beta L. Okay, And if you recall what Z naught is square root of L over C, and then beta is omega LC. And then you have an L, and then the C cancels, and then you have this being equal to approximately J omega L. Okay. So you can think of this as kind of a line inductance times a small length give you the effective inductor of this very short transmission line if you make it very short. That is reasonable if you do a sanity check. That if this line is very, very short, then if you were to send a current into this line, the current would be huge because it's shorted at this end. You could drive this, say, with a voltage source. And if this current is huge, it will produce a strong magnetic field, making this transmission line inductive. Okay. So what happens now if I let the other end of the transmission line be open circuited? In this case, ZL is equal to infinity. Okay, you can go back to your formula that we have derived previously for this general case. And if you make ZL infinitely large, this term will dominate over this term. And if you make ZL infinitely large in the denominator, this term will dominate over this term. And if you go through all the thought processes and drop the unnecessary terms, you will find that at this point, you have actually an impedance that looks like, let me see what I have now. That Z of minus L would be minus J Z naught cotangent of beta L. Okay, cotangent because I have a tangent in the denominator. Remember, if I go back and look at this formula again, I have a tangent in the denominator that when I invert it, it becomes a cotangent. So you will get this formula. Okay, and again, if you plot it, it will look something like this, that if this line is very short, it will look capacitive. And you can do a sanity check on that. Well, should it look capacitive? Well, if you have a very short piece of transmission line, if you connect the voltage source to it, there will be strong charge accumulation on this small piece of metal, and there will be electric field in between, and you have this kind of thing. And again, it goes to positive and negative, okay?